Good afternoon. My name is Roman Holland. I'm here for Cambustion, presenting on the DPG, the Automated Particulate Filter Testing System. Just to say a quick hello, I'm going to turn the webcam off now and begin with the presentation. So this is a sort of medium-length presentation covering the background of DPF testing, the challenges that it proposes, the DPG concept, and a quick look at the hardware, and then mainly focusing on the DPG applications such as loaded backpressure testing, DPF flow testing, filtration efficiency, regen mass limit, and drop to idle testing, catalytic activity and ashing, and then going into some more technical information about the DPG versions. And finishing up with some questions and a bit of a summary. So first things first, it's probably good to recap on what is a particulate filter. I don't know if anyone has previous experience in this. It's obviously quite obvious to us that work in the sector. So modern gasoline and almost all diesel vehicles are now fitted with particulate filters in their exhausts. These filters reduce particulate emissions by up to 2 orders of magnitude. There's a wide range of materials and designs of filters in use, but the majority look like the picture in this presentation, a kind of porous honeycomb or square cell design. They look rather like catalytic converters, except they're not flow through. The channels are alternatively flow on the inlets and outlets, forcing the flow through the porous walls. The walls and any soot previously deposited together filter out soot. So in essence, the soot filters the soot. There's quite a nice diagram or schematic of the theory behind a particulate filter. So looking at the challenges of conventional exhaust particulate filter testing, an engine's soot mass rate obviously varies with exhaust back pressure, which is dependent on the DPF load at the time. Ambient conditions and engine operating conditions. In the top left graph, there's a few examples of reference loads carried out on DPG, which gives you an idea of the correlation we can achieve, which is virtually line on line for reference DPFs. Two, there's obvious cost benefits. Often customers will come to me with wanting to free up their many test cells that are currently being used for DPF loading. So obviously loading on a transient dynamometer is very time consuming and obviously occupies very expensive resources. At Cambustion we have these dyno facilities, as we see in this photo. This is one of ours, but fortunately we're able to carry out a lot of our soot loads on our DPGs, which saves a lot of time. And then for an engine, exhaust flow rate, temperature, and the soot rate are not independent. They're all linked to one another. So it's very difficult to discriminate between which has an effect on the filter. Fortunately, a DPG can separate all three, allowing a wider range of testing to be carried out, but there'll be more on this later. So now this is looking at what's included in the DPG hardware or the concept. Including the DPG, there is a burner, a sort of heat and soot generator. Just lost my slide there. One moment. It's working. Soot monitoring and a smoke meter system. This is the blue box on the end, and a filter test housing, which we'll come on to later. And then there's various air control systems within the DPG, which is probably a bit too involved to go over now. There's a separate control PC included and containing the DPG control software, giving fully automated and customizable testing sequences. This is Windows 7 and Windows 10 compatible. The DPG will allow you to carry out testing over a full cycle, operating flows and temperatures to simulate an on-highway engine, automated and unattended execution of OEM standard or bespoke test protocols are obviously the sort of bread and butter. Here's just another schematic of the DPG. The principle of it is the airflow is actually sucked through the DPF or GPF. There's two main benefits of this. The entire air system is then below ambient pressure, so potentially poisonous gas leaks are inwards, not outwards, to the environment. The soot generator is also less affected by the buildup of back pressure across the filter. The vacuum will be created downstream of the filter, leaving the upstream burner relatively stable, close to ambient conditions. The DPG has three main air systems that merge into one. The primary and secondary airflows feed directly into the burner and therefore affect soot generation, whereas the tertiary airflow is added downstream of the burner. And this is the key difference that allows the DPF temperature and flow to be independent of the soot production. By adding a large electrical heater to the tertiary air system, we can independently put power in separate to the DPG burner. Now I'll talk a bit about the filter test housing. We abbreviate this to FTH. This allows uncanned, so bare DPFs or GPFs to be tested. This is particularly useful in our production QA applications, so or at substrate manufacturers and coaters. We actually now have 60 different shapes or designs of adapter to give you an idea of the uptake of the use of this product. So yeah, we use high temperature seals. This is the small green blob in the CAD drawing. This consists of a glass fiber fabric with ceramic fiber filling, and these can be used at high temperatures. But after regeneration, they're no longer reusable for loading purposes because they don't seal so well. There's a photograph in the bottom left of a typical GPF with one of our high temperature seals. We have a heavy duty FTH. This offers the ability to test up to 13.5-inch diameter filters. The principle is exactly the same, it's just a larger version of. Now we're going to talk about what the DPG can do, looking at the actual specific applications, starting with soot mass and backpressure testing, then some flow testing, filtration efficiency with both particle number and particle mass based systems, and the differences or similarities between them. Then look at some regeneration testing with soot mass limit or drop to idle testing, finishing up on some ash and poisoning, and then some R&D applications. So automated test capabilities. On the left-hand side is an example of a simple test schedule to determine the filter back pressure versus soot load. The test normally consists of a sequence of different modes like this, which are easily configured and modified to run automatically. For more complex applications, these schedules can be combined into longer programs which can run uninterrupted for days in some applications. On the right-hand side, we can see a soot mass limit program. This requires a sequence of soot loads which are increasing in their soot mass, followed by regenerations and then a validation based on filtration efficiency until failure normally. The program sequence, phase durations, pass-fail criteria can be pre-programmed within the software, making bespoke to each DPG user if needed. We're now going to look a bit closely at the soot-loaded back pressure. This is by far the most common application in a DPG. The soot-loaded back pressure curve itself typically has two main parts. The first is the pore filling, which is a very steep back pressure rise at the very beginning of the curve. And then as a layer, or a cake layer we call it, of soot over the pores is formed, the back pressure curve becomes less steep and enters the linear section of the cake filtration section. As the electron microscope pictures show, the pores are actually much bigger than the particles being filtered. So it's a common misconception that a soot particle is filtered out by small holes. It's quite the reverse. Initially, the particles penetrate deep within the pores, clogging up these pores as they fill. This is what gives us the rapid back pressure rise per unit mass. However, after these agglomerates of soot linked together to form a cake over the entry of the pore, the pressure rise is less steep per unit mass. The soot-loaded backpressure characteristic is used for estimation of soot mass on the filter in service, given a known flow. The pore bridging phase pressure rise is a strong function of the coating process and substrate pore size distribution. This should be monitored in quality control manufacturing. So there's some, just some quite nice photographs here of the exact same pore from clean to the cake filtration stage, along with a theoretical kind of graph of what is happening. On the right-hand side, we have some real data from the DPG, which shows what's happening quite nicely. If you have any questions on this, feel free to pop them in the little window. So the DPG can be operated as a flow testing rig. Often our customers have a blown bench rig, which is misleading. It's normally actually a suction bench, and we have the ability to correlate one of these to do equivalent flow tests over cold flow sweeps normally. So filtration efficiency measurement options based on particle number. The PN basis filtration efficiency measurement uses Cambustion dual diluter, which incorporates a TSI 3790 engine exhaust CPC. This has a 23 nanometer cut. The dual diluter has separate diluters for up and down stream concentration measurement. In the box there, this addition on the side of the DPG is the entire diluter and CPC instrument. This schematic here shows a disc dilution system, a rotating disc dilution system. The reason we need dilution is the TSI CPC is actually way too sensitive for DPG soot concentrations. Therefore, we dilute the sample with a known flow rate of HEPA filtered air to reduce the total soot concentration to within the CPC's working range. Having two separate discs, one for upstream and downstream, alleviates the need for a switching valve system between the upstream and downstream, which is obviously complicated and normally brings with it some particle losses, which no one likes. So filtration efficiency assessment. This is a typical FE curve based on PN measurement. This test was run at 2 grams an hour. This graph shows the filtration efficiency is heavily dependent on the amount of soot on the filter. A layer of soot is actually far more effective than the filter itself. Therefore, you need an instrument like a DPG with the ability to load the filter with representative soot in order to measure the performance of the filter. In terms of the effect of vehicle emissions, the most important part of the filtration efficiency curve is the first part, as it quickly improves the soot with soot load. We refer to this as the integrated penetration of the kind of blue striped section of the curve. This area is strongly affected by the pore size distribution, substrate and coating, and so it's where Q&A measurements are most concentrated. The stability of the filtration efficiency is a better indication for the damage level of the brick. For instance, if it's been dropped or regenerated quite aggressively, it will have cracks, which will drop your stabilized filtration efficiency down from 99.9%. Now looking at the same DPG, but an alternative to particle number counter is the smoke meter. Seen here on the end, this DPG is fitted with an AVL smoke meter. This measures the particle mass by measuring the amount of blackening on a reference white filter paper. This is also used for soot load monitoring. During the load, we measure the live concentration and if it varies at all. The filtration efficiency data is similar to the PN counter, but slower and less sensitive. It's often sufficient, and the instrument is far more robust and a lot cheaper, actually. Here's an example of a filtration efficiency curve produced by a smoke meter. We can see the data is non-continuous, it's discrete, instantaneous filtration efficiency measurements. but the curve itself and the penetration and the stabilized efficiency are very similar. So this is looking at a damage assessment of 5 different filters. This is using particle mass downstream of 5 different filters with different levels of damage. So obviously the lower of these will be the most intact filter. The smoke meter is ideal for detecting cracks or other damaged parts. As I mentioned before, this is a best asset with a known soot load on the filter. This graph explains this. These are the results from measurements of 5 filters ranging between undamaged and heavily damaged. We've plotted the concentration of particles passing through the filter rather than the filtration efficiency, so we can use a logarithmic scale. Thus, lower is better on this graph. You can see that once we have about 1 gram of soot on the filter, the filtration efficiency clearly reflects the level of damage. For the empty filter, though, this effect is dominated by the difference in the filter structure, and it's not possible to determine the damage. Now, I'll go on to talk about DPG Regeneration Simulation. Regeneration testing. So the DPG can simulate the flows and temperatures encountered during the regeneration process used to burn the accumulated soot off of the filter. This allows testing of the robustness of the filter to the thermal stresses in this process. So burning of the carbon soot causes very high peak temperatures within the filter, but also high thermal stresses as the soot burns at different rates in different parts of the filter. Typically, we see a hotter center and a cooler outer surface. The worst case thermal stress occurs during regeneration with a very low flow rate, high oxygen concentration in exhaust, and high temperature rise rate. In an engine, these 3 factors don't occur together in steady state conditions, and so the worst case stress occurs transiently in the so-called drop to idle event, or DTI, when an active regeneration is interrupted by the vehicle stopping. The DPG can simulate these events for R&D purposes, but for Q&A testing, we achieve a much more repeatable result with these 3 factors together. In order to monitor the thermal gradients, 0.5mm thermocouples are easily inserted into the DPF cells within the FTH. These thermocouple signals are all logged in the DPG, allowing us to record the temperature distribution in the filter within the same data set. The graph shows the temperatures recorded along the center line of a DPF at the front, middle, and rear. You can see the temperature at the front rises first, followed by the center, and then overtaken by the rear. When the filter reaches a high enough temperature that the soot begins to burn, the situation reverses and the highest temperatures occur at the rear of the filter, which produces high stresses by differential thermal expansion. So here's an example of a drop to idle simulation on the DPG. The worst case thermal stresses encountered when the airflow drops just as the filter reaches a high enough temperature for soot oxidation to start. The higher the soot load, the higher the temperatures encountered. Therefore, the soot mass limit in service is fixed by the resistance of the filter to the thermal stresses of regeneration. Properties of the filter and of the engine integration contribute to the risk of the filter damage. For substrate manufacturers, the DPG needs to be capable of simulating worst case DTI regeneration conditions to compare the resistance of different filters to repeatable operating conditions. The DPG can simulate these DTI flow and temperature conditions. And with the optional oxygen control system, or EGR system, we can also simulate the oxygen concentration effect. The peak temperature is very sensitive to drop to idle timing, so the repeatability of DTI testing is really not ideal for QA testing. It's only really an R&D tool. More on this. So this graph here is an example of a steady state QA test for thermal resistance with low airflow, high temperature rise rate, and an excess of oxygen. This generates temperatures high enough to trigger an exotherm and induce thermal stresses that can destroy a loaded DPF. The steady state regen is more widely used for QA testing because it's more repeatable than a DTI equivalent test. For those that are unfamiliar with the term exotherm, the graph above shows the temperature rise throughout the center line of a DPF during a steady state regen. It can be seen that the front face warms up first, above 600 degrees, the soot oxidation begins, and the energy released from the soot oxidation at the front begins a chain reaction effect. And this results in extremely high temperatures along the DPF, getting higher towards the rear face. There'll be a nice heat distribution map coming up to show this in more detail. So there's 6 slides I'm going to show that depict a complete DPF temperature distribution induced by steady state regeneration. The left-hand graph shows the 5 centerline temperatures as before. The right-hand graph shows the temperature distribution at the point indicated by the white line. At this point, the filter is being warmed up by the hot air entering the front. Therefore, the front is the hottest point and the center warms up faster than the edges. Oxidation is beginning now. We can see from the chart here that the sort of yellow patches where it's reaching 650 degrees. So oxidation will be kicking off at the inlet. The heat release from this oxidation is causing temperature to rise throughout the first part of the filter. Most of the filter is not yet hot enough for oxidation to occur though. A wave of oxidation increasingly rapidly moves through the filter. If we look for the white line here, we can see spikes beginning to occur. Moving on to the kind of final second half of the brick, the filter temperature is beginning to approach 1,000 degrees in the center. However, the very outer edges are still approximately 300 degrees C, which creates huge thermal stresses inside, and this, as the inside tries to expand more than the outside. In this graph, we can see the peak temperatures of the regeneration are being reached at the rear of the filter. The leading cause of failure within a DPF is either an axial or ring-off crack. The reason for plotting the axial and radial thermal gradients, which we'll see later on, is to try and relate these to failures we see from real-life exotherm tests. Typically, a DPF's thermal shock resistance is inversely proportional to its coefficient of expansion. So it's the difference in the expansion between the inside and the outside which causes the stresses and therefore the failures. Once the majority of the soot is oxidized, the temperatures reduce and even out, so the thermal stresses are somewhat reduced too. I touched on this earlier. So we've added some 2 extra graphs here. The thermal gradients can be calculated from adjacent thermocouples in order to resolve the peak thermal gradients. It's important that thermocouples are closely spaced. The thermal gradients in the axial and radial directions for the peak of the exothermic temperature rise are plotted in the 2 colourful graphs on the right-hand side. You can see that these are the highest towards the rear of the filter, and they're greater in the axial than the radial direction. The thermal stresses are dependent on both the large-scale temperature distribution and the local gradients, and are greater for filters with high thermal expansion coefficients. The distribution can produce either axial or ring-off cracks in the filter, which lead to poor filtration, or stabilized filtration. So we're now going to look at soot mass limit testing. The DPG can run automatic tests to determine maximum permissible soot load without damage to the filter in worst case regeneration. The test consists of running soot load severe regen FE tests. If the filtration efficiency is passed, the soot load will be increased by an increment normally 15%, and the cycle repeated until failure. This type of test can be left to run without operator intervention, which is popular with our production customers. We can see here, again, some centerline thermocouple graphs. 3 here, one at 8.5 grams per litre, incrementally increased up to 11.5 grams per litre. And we can see the height of the peak temperatures increasing test on test until failure. We're now going to talk a bit about challenges of GPF testing. So gasoline particulate filters, GPFs, technology is similar to the established DPF technology. There are very important differences affecting testing. The most important are a GPF undergoes continuous regeneration. This makes soot mass limit regeneration testing less important for GPFs. Lower soot equates to lower filtration efficiency. This makes very low soot mass filtration efficiency extremely important for GPFs. Diesel soot from a DPG is okay to test GPFs with. There's an analysis on this specific point later on. So low load filtration efficiency. For GDI engines, filtration efficiency at the near empty conditions is vital. The reason for this is to do with the in-service operating range of a GPF. The on-engine soot load is very likely to exceed 0.5 grams per litre, where stable filtration efficiency occurs. This can be seen again in the graph above, the stabilized Fe occurring probably at about 0.4 grams per litre, and the initial penetration occurring primarily all below 0.1 grams per litre. But yeah, there's a balance to be found here. You need to achieve high filtration efficiency without impeding the exhaust flow with a very high back pressure exhaust and then losing power. So it's a difficult game to be in. This is a comparison of GDI soot versus DPG soot. So both diesel and GDIs form directly from the atomized carbon in combustion process. It doesn't make much difference what the starting fuel was. The main difference is the amount of soot generated, so the concentration, and the DPG soot rate is therefore adjusted down to 2 grams an hour for GPF testing. Probably more importantly, the morphology or shape of the soot is very important for the behavior of the loaded filter, as it's the soot which actually generates most of the filtration. You can see from these electron microscope photos of the GDI, diesel, and DPG soot that the structure is very similar. It's made up of agglomerations of roughly a 20 nanometer primary spheres or primary particles. This is very important for the structure of the soot layer in the filter, which is why results from testing on a DPG are similar to engine results. There's more to back that up now. So we ran some standard testing cycles, and when compared against the DPG, these produced effectively identical back pressure, except for a very slight increase at high soot loads on the DPG. Yeah, this obviously corroborates what we said in the last slide. So now another application is catalytic coating activity testing. It's a bit of a mouthful. The DPG can be used to test for catalytic activity of a coated DPF or reactivity of a soot in situ on the DPF. The test can either be based on determining the oxidation rate by weighing the filter or by looking at the back pressure change, the gradient of the back pressure curve. Compared with tests based on weighing the filter, the pressure-based balance point test is much quicker and also fully automatic, no weighings. The balance point schedule uses a sequence of increasing controlled temperature conditions at a constant soot generation rate. At low temperatures, the back pressure rises constantly due to the increasing soot load. As the temperature increases, however, this begins to be outweighed by the oxidation of the soot. So when your back pressure curve is neutral or flat, you know that your soot mass rate is equal to your oxidation rate. The blue trace in this graph is for a filter without a catalyst. Over 550 degrees is needed for the oxidation rate to exceed the soot generation rate for the back pressure curve to start coming down. However, for a catalyzed or a coated filter, the orange one, this occurs at much lower temperature at 450 degrees. The balance point temperature is that where the back pressure line is flat. Normally the DPG produces, we're now going to talk about ashing of filters. So we have a new DPG fuel additive doping system, which we'll come on to in the next slide. But normally the DPG produces virtually 0 ash levels in normal operation. This is important for repeated testing of filters. However, by adding additives to the fuel, we can generate ash in a controlled manner. The ash interacts with the soot generation, so this kind of testing needs a soot generating system like the DPG. Ash is not removed from a DPF by regeneration in these settings, and so the ash accumulates over many loading cycles. This basically produces a progressive increase or a ratcheting in the back pressure, as shown in the graph on the left. However, the details are interesting. The right-hand graph shows the effect on the back pressure versus soot load curve for relatively low ash levels. While the empty back pressure always increases with ash load, it also accelerates the pore bridging process. So the pore filling pressure rise actually is reduced. This means that for some of the soot loads, a little bit of ash actually reduces the overall back pressure of the filter with no penalty on filtration efficiency, which is good. Here's a schematic of our new DPG fuel additive doping system. Ashing can be simulated using this doping system to inject oil directly into the fuel system just before the burner within the DPG. Oil additive packs typically include zinc, phosphorus, and calcium. The DPG ashing system allows a variation of the ashing rate during a schedule. It can also simulate ashing during a load and or during a regeneration. One of the primary advantages this has over doping your fuel is there's no contamination of your fuel system. So historically, we would put the additive directly into the barrel, but obviously this then poisons a whole barrel of fuel, and it involves flushing or purging through the whole fuel system when you want to revert to normal testing. Ash particles are completely different to soot particles in an aerosol sense. If the ashing additive is injected when the DPG is clean, not producing soot, then high concentrations of very small ash particles are produced, typically during a regen. On the other hand, if the ash is produced simultaneously with the soot during a load, then the ash material is mixed with the soot within the same particles. This produces the same effects as seen on engines, with ash deposition alone at high temperatures on clean filters, and co-deposition with soot in lower temperature operation. We're now going to talk about the oxygen control system. I'll refer to this as the EGR system for ease. This is one of the options we can include with the DPG. So normally in a DPG, we run an air system through the DPF with a much higher oxygen concentration than a typical engine, normally around a lambda 3. The EGR system can recirculate part of the DPG exhaust into the intake to control this oxygen concentration. And the concentration is monitored and automatically controlled by UEGO type sensors, much like you'd find in an exhaust pipe. The DPF inlet oxygen concentration can be controlled down to 2% in regeneration and loading conditions, simulating real or diesel engine operating ranges. This is particularly useful for DTI testing, where you want to simulate diesel engine conditions more accurately than a steady state regen. We're going to touch on different DPG versions. So we offer many different flavors of DPG, light, medium, and heavy duty DPG versions. They differ mainly by their fuel flow range, heater power, cooling capacity, and price. This affects the temperature that can be achieved at a given flow. What can be seen on the graph above. Different main blower options affect the maximum back pressure capability of the system, although don't be fooled into thinking heavy duty DPGs need more blowers. Often with larger DPFs comes lower back pressure. It's actually the smaller GPF filters that normally come with higher back pressure at a given flow. We also have options for PN filtration efficiency systems like we've seen earlier, ashing or EGR. I think we're coming to a bit of an end now. So this is obviously just a summary slide, looking at everything we've looked at, the applications, the improvements you can get from DPG, and the overall sort of benefits of the DPG. I hope this has given you an overview, and we'll try to answer any questions. If you can type them into the question section, that'd be great. So I will just finish on this note. There is an upcoming, if you've enjoyed this, you'll love this next one. There's an upcoming presentation on the AAC, the only truly mono-dispersed aerosol classifier in the world, classifying particles from 25 nanometers without charging. This is given by Dr. John Simmons. And also, we'd love for you to join us for our virtual conference given by Cambridge University on Friday, the 19th of June. I hope you pop this in your calendar. It's normally good fun for aerosol-related chat. If we could move on to questions now. I don't know if any have come in.
Okay. Yeah, so there's a couple of questions that have come in. Firstly, I had a question on about slide 17, actually. Can you go back to slide 17? Just clarification of what the filter damage we're talking about there is. So on this slide, we've got the results of the penetration of particles, that's the number of particles that aren't filtered out, via 5 different DPFs. Obviously, the undamaged one is the best. The other 2 that we're referring to there is the part at the top is really badly damaged, massively, almost destroyed to get that bad efficiency. The ones in the middle, the red line is a part where you can see the cracks. They're just small cracks, but they're visible by eye. The green and the bluey green part are ones where the cracks are so small and internal that you can only see them via an X-ray. CT is computerized tomography. So that's really minor damage that you can't detect by visual inspection. You can see by looking at the loaded filtration efficiency, but you could never see that by looking at the unloaded filtration efficiency. So you need something like the DPG for those. A second question we had is, so all we've shown here is uncanned parts that we put straight in the filter test adapter. Another question was, can we test like whole exhaust systems, which we can indeed, and there's plenty of specific applications that we haven't talked about here, where you might want to test a whole canned filter, or put the whole canned exhaust system, including maybe the filter and the catalyst in there for some applications. So if we take the FTH out of the test section of the DPG, then you can put any kind of exhaust system in there. We'll provide the flanges, and it's just a welding job. Final couple of questions were, how do we determine the amount of soot on the filter? So if you, on the soot loaded backpressure graph, for example, all of that's dependent on the soot mass on the filter on the bottom. The answer to that is normally we weigh the filter in order to determine the amount of soot on it. So we weigh it at the start of the test, and it's weighed at the end of the test. That weighing has to be done hot, but that's all, warming the part up for that is all part of the automated schedule. And so that's the normal method of working out how much massive soot there is on the filter. The second way of doing it is with the smoke meter instrument that Ryan mentioned earlier. That we can use the measurement from the smoke meter to tell us how much soot we put on the filter as well. So there are 2 choices there. The latter one has the advantage that it knows doesn't need any human intervention. So the tests based on the smoke meter can just run entirely unattended. And that leads me on to the final question, which is how many people does it take to operate the DPG? And the answer there is basically less than 1. You need people to start the test, load the filters in the first place, but then the majority of these tests go on for an hour or 2, most of which time is unattended, and they operate fully automatically, with quite a lot of degree of automation in the reporting the results as well, as Ryan mentioned. So normally the personnel operating this can do a lot of other stuff as well. So that's all the questions we've had.
Okay.
So I think, should we say goodbye?
Yes, thank you for joining. I think we'll end it there.